just to start, can everybody hear me also at the back of the room? Because I usually, yeah, I have a very low tone of voice. Is there a microphone I can use or no? Okay. If you don't hear me, just show me. Anyway, to start, how do you usually do anatomy? If you're interested like in gross anatomy or well, the microscopic characteristic of the human body. This is what I call the old school, right? So this is my tribute after spending 7 years in the Netherlands. This is the Rembrandt anatomy lecture of Dr. Niklas too. And typically, to learn about anatomy or neuroanatomy, you need 3 things, right? The teacher that explains you the stuff, so the professor, the book from which you derive all the knowledge, and most importantly, the guy in the middle, the cadaver, right? Which is probably from an ex-convict and something that you could sacrifice, well, it has been killed, and then you can, well, basically look at anatomy. And also the nice thing that you can see in this specific painting is what also interests most of us as neuroscientists, is that we try to connect structure and function, right? So the professor is showing the muscle, saying this muscle is responsible for making this movement, right? So this is the link, this is one of the most interesting links from the neuroscientific point of view. Nowadays, we just need to spend a little bit more money, but we can get these fantastic machines, the MRI scanners, right? And what these scanners allow us to do is that we take the cadaver out of the picture finally, and we can start doing neuroanatomy in vivo at an unprecedented resolution, right? And with multiple contrast as well. So here, what I'm showing you is, well, a typical MRI scanner on the left-hand side, and then I'm putting you 2 axial slices from the same brain, telling you that basically what we can get from the MRI scanner is with the same machine, we can get different tissue contrasts, right? So these are the most typical tissue contrasts that we can get, the T1 and the T2 weighted scans, and you see that already it becomes pretty clear to separate the 3 different tissue types, right? So corticospinal fluid in the ventricles, deep white matter being hyperintense here on the T1, and gray matter being slightly darker on the T1, and a different contrast, almost flipped, completely flipped, on the T2 weighted image here. So same brain, same machine, but different kind of contrast, different kind of neuroanatomical information. These images are typically in the range of 1 millimeter isotropic, and if we think, well, based on what we know from these kind of pictures, so from electron microscopy picture, we know that in each and every of these voxels, which is how we call the spatial location in the MRI images here, which is a 3-dimensional pixel, effectively. We know that inside each and every one of those, we have thousands of myelinated or unmyelinated deep white matter, like in that case, axons, right? And at least when it comes to diffusion MRI, so from my specific point of view, so from the specific point of view, what we're going to talk about today, these are very helpful for us because they do act as barriers and as cables, right? Because they're nicely organized, tightly packed together, and they follow a certain orientation. They make it such that the water molecules will preferentially diffuse along the orientation of the axon rather than perpendicular to it, right? And now we're going to see in the next couple of hours how we can use this information to probe about neuroanatomy in vivo. Because what we're doing effectively when we acquire MRI data, is that we're looking at these guys. We're looking at water molecules, right? That's where the contrast comes from. We're not getting any signal from the neuroanatomical substrate per se. We're not getting any signal from the axons, but we're just getting signals from the diffusion of the water molecules. And since we can do that, now we can start playing, now we can start identifying once again the 3 tissue types that I talked about before. So we have free diffusion, once again in the ventricles here. We have a slightly, well, still free diffusion, but more constrained in gray matter because of the cell bodies, glia, and so on and so forth. And most importantly, most interestingly, at least for the beginning of this talk, we do have diffusion in white matter that shows clear anisotropy. So a clear orientational preference. Because once again, of these tightly packed axons, the water molecules will diffuse more preferentially along the axons, right? So this is when we talk about diffusion anisotropy. And we mean that it has a directional, preference. And knowing this, assuming these different behaviors of water molecules, these 3 tissue types, for example, what we're most likely interested to do is to sample a 3-dimensional space using n orientations. So I want to see for each and every orientation in a three-dimensional space how water molecules diffuse. Do they like in that specific location, do they like to diffuse along this orientation, and so on and so forth, right? And when we do that, this is what we get out of our scanner, right? So we can play, there are two main parameters in diffusion MRI. One is orientation, so spatial encoding, and the other one is the B value, so the diffusion contrast. And here I'm showing you like 6 different images. In A, you have the so-called diffusion encoding gradients, which are completely turned off. So I'm not looking for diffusion in the first image, and that is just a typical T2 contrast, what I discussed, what I showed you about before. Now, what happens for the green dots? So when I probe diffusion along 2 different orientations, along the x-axis and along the z-axis, well, what you see here, what you should be able to see here, is that given the same slice, given the same axial slice, if I probe 2 orientations, the contrast of the same image change, right? So I'm looking at the same thing, but now I start having directional encoded information, right? And if I play with a B value, so with a so-called diffusion contrast, you see that from the minimum, so from D, from a B value so-called of 1,000 to 3,000, I get lower SNR, so it becomes more tricky to, well, even see that there's a brain in those images. But you see that it becomes more clear, the contrast to noise ratio. So you see that the hyper-intense areas become more intense, and the darker areas become more, well, darker, the higher the B value that I get. And it's basically like in photography, when you leave a shutter open for more time, you capture more light. Here it's the same thing. We listen to the diffusion signal for longer, and we capture more diffusion, right? That's how we enhance our contrast to noise ratio. And now what we want to do, given these images, is to try and go back, right? Is to try and understand, try to link these images to the neuroanatomical substrate that we know is there. And how do we do that? And the answer is with math, a bit of modeling. So I hope I'm not scaring anyone away already. But what we want to do with modeling is that we say that given the signal S for a certain orientation G and for a certain B value B, we try to link that with a signal with no diffusion encoding, so S0, and the exponential of, once again, the B value, the orientation G, and then you see the D, which is the so-called ADC, apparent diffusion coefficient, that will become later on in this slide the so-called diffusion tensor. So that is what we try to estimate. We try to estimate, again, in every voxel, that quantity D, which can be either a scalar, so a diffusion coefficient, or a diffusion tensor here. And just by this very simple equation, if we apply that and if we can recover D with some math, we can do some pretty spectacular things, because we can construct an equisurface, well, an equiprobability surface of diffusion, like I'm putting here, that will allow us to, well, once again, distinguish between the 3 basic tissue types that we have, and will also give us the so-called principal diffusion direction, right? So given the D, which in this case is going to be the diffusion tensor, I can now start to put these vectors into each and every voxel that I've acquired, right? So now I have the information that here, water molecules tend to diffuse from the front to the back of the brain, right? And so on and so forth for all the other spatial location. And we go back to the original assumption, is that now we say that this principal diffusion direction should correspond to the orientation of the white matter fibers throughout the brain. And given this assumption, we can start connecting the dots. So we can start from the left hemisphere and follow connecting all the dots, all the vectors along the path. And if we do that, we do what is basically known to be a structography, right? So we can extract now from an in vivo sample, an in vivo human being, we can start constructing the long-range axonal connectivity in a non-invasive in vivo fashion, right? So we can have the callosal fibers, like in this case, connecting the 2 hemispheres. We're not just limited to that, so we're not just limited to the structural connectivity aspect, but what we can what we can also derive from the diffusion tensor and other techniques that are available using diffusion MRI data is that we can infer, we can describe microstructure. Microstructure being the characteristic of the white matter axons that we have acquired that belongs to this specific sample. So from, for example, the most typical measures that are derived from the diffusion tensor is the so-called fractional isotropy, mean diffusivity, axial diffusivity, and radial diffusivity. Axial diffusivity being the amount of diffusion along the principal diffusion direction, and the radial diffusivity being the amount of diffusion perpendicular, so the D perpendicular, in respect to the to the white matter axons. And FA effectively telling us how sure, how confident we are about the estimate of our principal diffusion direction. Right? This is why it becomes much more intense in white matter. It becomes easier to distinguish white matter in respect to all the other. Because in white matter we have, once again, the densely packed axons, and the principal, it's going to be easier. We're going to be much more sure about the estimate of the principal diffusion direction than anywhere else in the brain. Again, we can apply the same tractography rationale that I just described before to extract several white matter bundles from the brain in vivo. So those related to language, those related to motion, sensory information, and so on and so forth. And we can start building in vivo atlases for all the subjects that we acquire. So that in the end, what we can do with computational diffusion MRI are mainly these two aspects. So we can do in vivo virtual histology, but we can also do in vivo virtual dissection. So the structural connectivity information and the microstructure information. Right? These are the two main aspects, these are the two main goals when it comes to computational diffusion MRI data modeling. So this was just a very quick and brief introduction. This is what we're going to cover today, at least in the first part of the talk. Give you an idea of what is diffusion and how we actually acquire the data. So we perform diffusion-weighted MRI. The diffusion tensor model, which I just now briefly hinted at, and DTI. Then we're going to go to the distortion correction, specifically for diffusion MRI, all the way down to how you should perform automated quality control once you acquire your data. If there are any questions at any time, just raise your hand and let me know. We can make this interactive. So as soon as something is not clear, just ask. Anyway, what is diffusion, right? So diffusion was first discovered by Robert Brown some time ago, and it basically describes the random motion of water molecules given a certain temperature, right? So they lie perfectly still at absolute zero, but the human body is at around 37 degrees centigrade, so water molecules tend to randomly diffuse with a certain diffusion coefficient, right? So he first observed this phenomenon. The person who actually formalized it, so put this down into an equation, was Albert Einstein, describing the mean square displacement as being dependent both by time and on the so-called diffusion coefficient, which is what I already have talked about in the brief introduction that I said. So that being this equation valid for any homogeneous barrier-free, so without barriers, so without the axons that I just described before, the longer you wait, the more diffuse you're going to observe of your water molecules, right? And this, of course, follows, as you can see here, sort of a Gaussian profile, two-dimensional Gaussian profile. So, exactly like I said, another way to basically describe exactly the same equation as before is that diffusion displacement, well, an ensemble of water molecules diffusing can be modeled using a normal distribution with zero mean and a standard deviation equal to 2 time and diffusion coefficient. Zero mean displacement, so that's the mean of 0. And again, like I said, you have a double dependence, one over time, so how long you're willing to wait to observe a diffusion, and the diffusion coefficient itself. Why are we interested actually in observing this diffusion? Or we go back to the original introductions, right? We have said that we can easily at least identify, easily think of at least 3 different behaviors of diffusion in the 3 different, well, the 3 basic tissue types that we have in the brain, right? So we talk about purely free diffusion in the ventricles, We can identify diffusion in gray matter, restricted but still relatively free. And then we can talk about anisotropic diffusion in deep white matter. And the nice thing of this, why this works, is exactly because given the prototypical representation of a myelinated neuron, the axon acts as a barrier, right, for these water molecules. And if you were to look at the same kind of simulation profiles that we described before, we can see that the longer you wait to give it a certain diffusion coefficient, those are the three different displacement profiles that you will experience in the three different tissue types. Being the anisotropic sort of cigar, giving you this cigar shape, showing you the anisotropic behavior of water molecules. So one thing is performing sort of a more chemical experience in which you're actually interested to measure the diffusion coefficient of different fluids. Another thing is deriving the diffusion coefficient from an MRI experiment, right? And this is why we talk about, actually, when we talk about diffusion MRI, we talk about apparent diffusion coefficient, right? It is apparent because it is dependent on the settings that you impose on your MRI scanner. So, given two different scenarios, let's say, in which you have totally free diffusion and another one in which you introduce a barrier, like it can be, for example, two axons very close to each other, and a single water molecules that can diffuse throughout a certain amount of time, you see that if you were to record your signal after a very brief time, the two displacement profile look almost identical, right? But if you're willing to wait a little bit longer, you see that these water molecules, the delta X of these water molecules, will definitely be bigger than the one you experience when you start inputting some barriers. So if you're willing to wait a little bit longer, now you can distinguish between the two different scenarios that we have here. One being totally free diffusion, and the other one being diffusion with actual constraint. And again, this is exactly then why we talk about apparent, right? Because given the different time that we set on our scanner, we can mathematically estimate the diffusion coefficient at every spatial location in the brain. How do we practically do this when we sit behind the scanner console? Or what happens from the acquisition sequence point of view? This is from what happens from the physics point of view, right? So this is the actual sequence that you use when you're interested in doing a diffusion MRI experience. It's the so-called pulse gradient spin echo sequence. And what it basically uses, forgetting about the 90 and 180 for now, it uses these two diffusion encoding gradients. But basically what they do is that the first one labels the water molecules at a certain spatial location. You wait for a little bit, and then you try to relabel, to basically recall the same water molecules that you've labeled before. Now, why does this work? What is the assumption here? If you label the water molecules at this time point, and they didn't diffuse, they're still there along that certain orientation, then you can cancel out the original labeling that you performed. On the other hand side, if you have labeled some water molecules, they have diffused along a certain orientation, and you try to cancel out exactly the same water molecules that you labeled before, they're not going to be there anymore. They have diffused, right? So you're not going to recover your signal, basically. This is why when we observe actual diffusion, so when diffusion happened, we talk about signal decay, because you cannot recall exactly the same signal that you sampled before, just because the water molecules are not there. That's why you see that the signal from the initial T2 intensity decreases along a certain specific orientation. And another information is that these two gradient encoding are direction dependent, right? So these two gradients will have an XYZ encoding, so that you can say, I'm interested in diffusion along a certain X vector. And at the typical time scale that we use in diffusion MRI, so typically in the order of millisecond, we are capable of using this sequence to, probe diffusion in the order of 30 micron, right? So we can use the microscopic machine to probe diffusion of water molecules at the microscopic scale, right? Which is quite powerful thing to do. There are two main parameters that you want to set at the scanner when you perform a diffusion MRI experiment. And one is the so-called B-value that gives you, once again, an idea, like I introduced before, of the diffusion weighting that you have. And this is dependent on the gradient strength and on the diffusion time. So the diffusion time being the longer you're willing to wait for diffusion to happen, and the G, the amplitude, is the amplitude of the diffusion encoding gradients that I described before. And let's say that we keep G constant in this case, and we vary the diffusion time. So once again, you wait longer, the bigger the B-value is for diffusion to happen. You see that at the B equal to 0, we go back to our standard T2 weighted image. And the more we increase, the lower the SNR, the signal to noise ratio. So it becomes more tricky to distinguish the tissue boundaries here. But the bigger is the contrast to noise ratio. So the easier it becomes to distinguish between deep white matter areas that show a certain diffusion encoded orientation versus all the other gray matter or CSF areas. And the other parameter that you set up at your scanner during the acquisition is the so-called gradient direction, right? Which can be a three-dimensional vector X. And now we see basically the same example that I gave you at the beginning, but with more information. Now, keeping constant the B-value, in this case, so setting a B-value of 1,000, now what we do is, given the same axial slice, we start playing with the diffusion encoding orientation. So we start looking for, well, effectively preference of water molecules to diffuse along different axes. And then we have diffusion along X, along a certain diagonal, the opposite diagonal, and along the orientation Z, so the one that comes out of the screen. Right? So if we look at, for example, the two extremes, so diffusion along X, right? So from left to right, versus diffusion along Z, you see that especially this area on the back here completely changes the contrast, right? What this basically means is that if you remember the labeling that I just described before, in these areas, water molecules will tend to preferentially diffuse along X, so that they're not there anymore, and the signal has decayed, right? So we can already say that what happens in this area is that axons are probably oriented along the left-right axis, right? But definitely not along the Z, right? Because here we get exactly the same signal intensity that we had at the beginning, right? Look at the diagonals here. We have signal dropout for this diagonal, so the axons do a sort of a U-turn, and the same thing on the opposite hemisphere, right? But if you look at these two diagonals, then you see that the other part of the corpus callosum is still, well, right, hyperintense, right? So this is exactly the kind of information that we're playing with here. And because specifically of the way that we get this contrast, we talk about an isotropic measurement in white matter. While if you look at, once again, the CSF, so the ventricle areas, is consistently dark across all of the four orientations that we sampled, right? Just because water molecules vary, it's free to diffuse in any possible orientation, right? So the water molecules that I labeled at the beginning are definitely not going to be there anymore. And that's why we talk about free diffusion in that area. How does this translate in practice? So from the signal profile point of view, and from also a typical acquisition point of view, what you typically do when you set up a diffusion MRI experiment is that you, well, effectively acquire some B0 images interspersed into your acquisition, and then you acquire a certain set of diffusion encoding orientation to sample, well, efficiently sample a three-dimensional Cartesian space, right? And those are the kind of images that you will get out of the scanner. If you now consider a single voxel, so on the crosshair, on the axial slice on the left-hand side, this is what you're going to get. In respect to fMRI, or to a typical EEG acquisition, on the x-axis, you don't have time. So it's not the signal profiles that varies with time, but it's the signal profile that varies with volume. Volume being a different orientation that you're probing diffusion for. The highest peaks, of course, correspond to the signal at V0, so when you're not probing for diffusion, when you switch off the diffusion encoding gradients. And the smaller signal here describes, you give that information about the anisotropy of white matter, well, of white matter fiber axis at that specific spatial location. If you look at a different area, so in deep white matter on the frontal part of the brain, you see that the signal profile changes, right? So different spatial location will show different diffusion preferences, different diffusion signal profiles. And given that you're looking either at the ventricle area, so CSF or white matter, also the intensity, also the signal range will dramatically change. And these two changes, these two relative changes in respect to the original signal that you sample at V0 depends on the so-called apparent diffusion coefficient, which we talked about before. So, to give you just a brief summary of what we discussed as a brief diffusion MRI introduction, the images that you acquired, like I said, with a certain gradient encoding will show contrast along the same gradient encoding direction. When actually in that spatial location you have a certain amount of diffusion, the signal is going to be reduced in respect to your baseline. Crucially, in white matter the measures are anisotropic because of the axonal background that we have, and in gray matter and CSF we talk about isotropic diffusion. So moving on to the most basic model that we can use, is there any question about what we just saw so far from the basic diffusion MRI principle, or is it everything? Yeah? All right. So moving on to the basic modeling approach that we have at our disposal to analyze this kind of data that I just described. This is the so-called diffusion tensor imaging, and we're going to see, well, how diffusion behaves in different brain tissues, apparent diffusion coefficient again, specifically the diffusion tensor model, and which measures you can derive from the tensor itself. So diffusion tensor imaging, how does it work? We have our standard set of images. So you've performed your acquisition, you acquire the data from your well-behaved subject, collect the data, and now you want somehow to analyze them, right? We have our V0, we have our diffusion encoded slices, and we set behind the computer and we want to do the initial thing that I showed you before, so estimate the principal diffusion direction, do tractography, and so on and so forth. The basic assumption behind the diffusion tensor model is that diffusion can be described, well, diffusion within all the tissue types that we have can be described with a single bell-shaped Gaussian model, right? But instead of being in the nice environment described by Einstein at the beginning, so a barrier-free environment, we do have, well, we do encounter the barriers, the anatomical barriers that we have inside our brain. And therefore, we should take into account the covariance that comes out of the anisotropic behavior of water molecules. So now, if we want to describe diffusion, we cannot just use a single scalar, so a single number in every voxel, but we need to use something more. We need to use a matrix. We need to use the so-called tensor, right? So that, once again, from a more statistical point of view, we have a three-dimensional Gaussian distribution with, once again, mean zero, so centered, time dependence, and now this capital D becomes in bold, represents the matrix that we're interested in. You fit this model. What you effectively do when you do diffusion tensor imaging is that you effectively fit this model into each and every voxel. Now, this is the basic equation, right? What are the knowns and unknowns in this equation? Well, the most basic one, what you always do when you do modeling, is that you acquire a certain signal and you want to derive the information that are completely unknown to you, right? So on the left-hand side of this equation, you have what you just sampled, which is the signal measured after applying a certain diffusion encoding gradient along direction J, right? So for each and every diffusion orientation that you sample, for every J diffusion direction that you sample, you have a certain signal intensity, right? Which is the profile that I was showing you before. The other thing that we know is that for the same spatial location is the signal measured without any specific diffusion encoding applied. The other two things that you set behind the scanner, like we said before, is the b-value, so the diffusion the diffusion sensitivity that you want to give to your acquisition. And then you also know, effectively, the unit vector that represents that diffusion encoding orientation J that we just talked about before, right? So all of these parameters are known to you, by definition, by you sitting behind the scanner and setting it up that way. Now, what you don't know, is the actually 3x3 diffusion tensor. This is what we're trying to estimate here. This is what we're trying to put into each and every spatial location. And what the tensor effectively is, what the capital bold D effectively is a 3x3 symmetric matrix. So, meaning that what you need to estimate are 6 unknown parameters, right? Which are the parameters along the diagonal. So the apparent diffusion coefficient sampled and recovered along direction x, y, and z, and the diffusion sensitivity probed along x, but sampled along y. Now, what that effectively means is that the off-diagonal elements represent the correlation, the covariance of diffusion ampling along different axes. So what happens if I sample for diffusion, I originally sample for diffusion along the x-axis, but then I listen from a direction perpendicular to it, right? Will I still see some changes, or will I not? Right? And of course you can represent those scalars in two-dimensional maps, like we did for all the microstructural parameters before. Now, of course, the crucial question is why do we need to go to this more mathematically sophisticated approach? Why do we need a matrix, and it's not enough anymore to just have a single scalar in every voxel? Well, imagine two very simple cases, right? You are in a certain voxel,